Hello, and welcome to this recorded e-learning about Virtex-6 clocking resources. My name is Frank Nelson. I'll be your instructor for this module. This module introduces the clocking generation capabilities in the Virtex-6 FPGA device family, including its clock routing and clock management resources. This module is designed to enable you to get the most out of these resources. Virtex-6 is a brand new and leading-edge FPGA architecture. After completing this module, you will be able to detail the clocking resources available as part of the Virtex-6 FPGA device family. You'll also be able to specify the resources available as part of the clock management tile, frequently called a CMT, and describe the basics of the PLL's functionality. Virtex-6 has three different clock routing resources: global, low skew for regional clocking, and I/O clock routing resources which are designed for the highest speed. Now we'll talk about the specifics of these networks a little later on. We'll also talk about all these resources and explain when you want to use each of these resources. Now the clock region structures are still important with the Virtex-6 device family, unlike the Spartan families. Note that the clock regions now contain 40 CLB rows, not 20 as in the Virtex-5 device families. Virtex-6 also has clock management tiles called CMTs, which include PLLs and some extra features. Unlike Spartan 6, Virtex-6 does not contain a digital clock management resource, or DCM. The DCM behavior is completed by the PLLs that are part of the CMTs. Now there are up to 9 CMTs per device, depending on your device density. The CMTs perform frequency synthesis, clock deskew, and jitter filtering. Basically everything a PLL and a DCM has done in previous device families. Now, the MMCMs accept a very high input frequency range from 10 to 800 MHz. This is a very wide range and allows very flexible frequency synthesis. The VCO frequency has also been improved in the PLL. It now supports up to 1.6 GHz. Like the DCM and the PLLs and other FPGAs, customization of the MM resources is still done with the clocking wizard. The MMCM has 8 independently programmable counter or programmable clock outputs. These outputs are primarily from a counter 0 to counter 6+, as well as the clock feedback output. These are added specifically among counter 0 to counter 3, which offer complement outputs. This allows a 180-degree phase shift of the outputs automatically, while requiring a minimum set of the counters. Additional MMCM features include the clock input switching functionality, phase shifting, fractional clock division, and the dynamic reconfiguration port. Clock switching allows you to seamlessly switch between the clock in and clock to without resetting the MMCM. We'll talk about these features in more detail a little later. There are also 2 kinds of software primitives: the base primitive and the advanced primitive. The advanced primitive will give you access to the advanced features and allow clock switching between 2 clocks without burning a second BufGmux. This slide represents the die view of Virtex-6. The yellow bars are I/O columns. The blue bar is the central column. The column contains the MMCMs as well as the global clock routing resources, which are shown in green. The clock regions are organized into flat rectangles that are divided down the center of the FPGA by the central column. In this case, the black line separates the regions so that an equal number of CLBs is above and below the horizontal routing, commonly called H rows and shown here as buff H's. There are between 6 and 18 clock regions in the Virtex-6 FPGAs, depending on the device density. The global clock buffers, or buff Gs, are in the middle of the chip. These drive the vertical spines of the global clock network. The horizontal spines of the global clock network run through the middle of each clock region. The horizontal spines are driven by buff H buffers. There are also regional clock routing resources called buffrs. In addition to the clocking elements in a single region, a buffr can also drive clocks into the neighboring clock regions, one above and one below, so they are more than just a regional clocking resource. Clocks are driven up and down from the center row, the H row, of each clock region. The buff I/O buffers are placed within the I/O column and are designed to be high performance and thus highly optimized routing placed very near the I/O columns denoted in yellow. Some buff IOs are capable of spanning multiple regions. Each device has 2, 3, or 4 I/O columns depending on the device density. This provides 1 or 2 columns of I/O pins per clock region. Note that the I/O pins associated with each column and a single region have their own I/O bank. Note that the MMCM tiles are associated with 2 clock regions, so ideally those MMCMs would be used to create the control signals associated with the neighboring clock region. This behavior of isolating the MMCMs, a single clock region, with a fixed number of CLBs and a fixed number of I/O pins, and a single I/O bank, is reflective of an ASMBL architecture. This is a characteristic Xilinx has used with Virtex-6 device families and basically implies that as the density of the FPGA increases, you basically get a fixed number of additional regions as the density grows. This is a close-up view of the Virtex-6 FPGA clock region. Each clock region is 40 CLBs high and half the width of the device. Each clock region contains 12 buff-H buffers that drive the global clock network. Any 12 of the 32 buff-G clocks can drive the buff-H resources in each region. Each clock region has 6 regional clock networks, driven by the regional clock buffers in the local region or either of the neighboring regions. Each clock region has up to 8 I/O clock networks per I/O column in the region. A clock region can have 1 or 2 I/O columns. There are 4 local I/O clock networks per I/O bank, driven by the I/O clock buffers in that bank. There are also 2 additional I/O clock networks driven from the bank above and 2 from the bank below, except in clock regions on the top or bottom of the die. This makes a total of 8 I/O clock networks per I/O column, and since each there are 2 I/O columns, for a total of 16 I/O clock networks that can be used in the region. Virtex-6 has a large global clock network that provides the distribution for up to 32 global clock signals across the entire FPGA. These reside in the center of the die, but this is not relevant to the designer since clock routing is handled by the tools. To bring these clocks into the device, there are 8 global clock input pins, but these are not the only pins that are available to bring a clock into the FPGA. There are also 4 clock-capable I/O pins per I/O bank. The 32 clock buffers are placed on the die such that 16 are on top and 16 are on the bottom, but this only matters for certain connections to the buff-Gs. The 32 buff-Gs each drive 1 vertical spine of the global clock routing resources. To reduce the clock skew, they actually drive to the center of the top half and center of the bottom half before fanning out to the H clock rows. But like I said, the routing of the clocks is handled by the tools, so don't get too preoccupied by this. The global routing resources, or buff-Gs, can be driven by 8 global clock pins. There are also 4 clock-capable I/O pins per I/O bank, 4 that are differential or single-ended. The global clock pins are not the only clock input resource. Now, all 32 buff-Gs reside in the center of the device, as I mentioned. The buff-Gs can be driven by global clock inputs, clock-capable I/O pins, which is located in the inner I/O columns only on the die. That's important if you're planning your pinout. The MMCM outputs, other buff-Gs, general interconnect, regional clock buffers, or buff-Rs, as well as the outputs of the GTX transceivers. The buff-G outputs can drive the vertical global clock spine. Also, the buff-G control component implements a glitch-free clock switching between 2 sources and operates a clock enable for disabling clocks if so desired by the designer. Please note that the buff-Gs can only be driven by clock-capable I/O pins that are placed in the center I/O columns. This is important again for planning your pinout. For many years now, we have referred to the buff-G as a number of different primitives. This includes the buff-G MUX, which is supported with Spartan 6, as well as the buff-G control features, which is supported with Virtex-5. Now, Virtex-6 supports the latest features of the buff-G control, which we'll discuss a little bit later on. But basically, any feature in the past that we've associated with the buff-G is still supported with Virtex-6.